Well, thank you. So my role here is to facilitate a discussion about the interface between string theory, particle theory, and cosmology. So I hope it will be a fun session. I'll first make 5 minutes remark and then ask 4 panelists, Nathaniel Craig, Eva Silverstein, Grant Remen, and Irene Valenzuela to each give 5 minutes remarks to present variety of perspective about the interface. And I'll ask the audience to allow these panelists to speak without interruption. After each of their remarks, I'll have them take questions from the audience. And when they are all finished, I'll open the floor for unstructured discussion. So that's the plan. So I'd like to pose these 3 questions. Are there universal constraints on the low energy limit of string theory? If so, are such constraints relevant to particle physics and cosmology? And what are interesting questions in particle physics and cosmology that string theory may try to solve? So I sent these questions to the 4 panelists last week so that they would know in advance what this discussion session is about. Okay? Before I'll begin by pointing out that there are reasons to believe that the Wilsonian paradigm of low energy effective theory needs to be modified for gravitational theories. I'll show you a concrete example of low energy effective theory that may look consistent but do not have ultraviolet completions. I'll argue that the answer to the first question is yes. The first exhibit that I'd like to present in support of this claim is the fact that every continuous parameter in gravitational theory is an expectation value of some dynamical field. In the ADS-CFT correspondence, this statement can be proven as follows. If there is a continuous parameter in gravitational theory in ADS, there is a corresponding parameter in dual CFT. Such a parameter must be associated with an exactly marginal operator in the CFT, which then corresponds to a massless scalar field in ADS. This means that although one can formally write a low-energy Lagrangian with a continuous parameter in the gravitational theory in ADS, such a low-energy theory does not have an ultraviolet completion without a corresponding scalar field, since ADS-CFT correspondence demands scalar field for each parameter. My next exhibit is the structure of the space of such parameters, namely the moduli space of string vacua. In this context, I gained some notoriety 17 years ago when I proposed a set of conjecture with Qumran buffer called the distance conjecture on the basis of what was then scant evidence. Over the past 17 years, our conjecture have been tested and verified in a numerous string theory construction, as Irene tried to tell you yesterday, although she didn't have enough time to do that. In the ADS-CFT correspondence, we can translate the distance conjecture for gravitational theory in ADS into statements about the moduli space of conformal field theory, which is called conformal manifold. So, last year, Baum and Calderon Infante proved some such statement. In particular, they showed that for conformal field theory in 3 and more dimensions, if there is a point in the conformal manifold with enhanced higher spin symmetry, the distance to such a point measured by the Zamolodchikov metric is infinite. It's always infinite. Therefore, although we can formally write a low-energy Lagrangian that generates higher spin symmetry at finite rather than infinite distance in its moduli space, such theory cannot have consistent ultraviolet completion. Our distance conjecture also claims that as we approach the infinite distance limit, say phi goes to infinity, a tower of light particle appears whose mass vanishes exponentially. So the mass goes like exponential minus alpha times phi or some positive constant alpha when scalar field phi is canonically normalized. Okay? For quantitative predictions, for many applications, it is important to determine this constant alpha, as Irene was saying yesterday. Recently, Yifan Wang and I were able to derive a universal formula for alpha for a class of ADS-CFT pairs, including non-supersymmetric cases. And I plan to discuss this new work in my talk at the conference associated to this program in the week of April the 1st. So far, I have discussed the scalar field with a flat potential. With some non-trivial potential, Asmund Folkestad has constructed initial data which violates the Penrose inequality in ADS for theories satisfying the null energy conditions. As shown by Nette Engelhardt and Gary Horowitz, bulk theory violating the Penrose inequalities are incompatible with the ADS-CFT correspondence. Therefore, Folkestad's work shows that there are non-trivial ultraviolet constraints on scalar potential in low-energy theories. Asmund is Netta's student, and Netta was Gary's student, so it took 3 generations of physicists to come up with this example. There are also constraints on symmetries of low-energy effective theory of gravity. More than 50 years ago, John Wheeler conjectures that there are no global symmetry in quantum gravity. In the 1980s, this was shown for perturbative string theory by Tom Banks and Lance Dixon. More recently, it was proven by Daniel Harrow and myself using the ADS-CFT correspondence. The weak gravity conjecture strengthens this statement about no global symmetry. In ADS-CFT, Ofer Haroni and Eran Pauti showed formulate the weak gravity conjecture as a charge convexity condition on conformal dimension of CFT primary operator, like this kind of convexity properties. Although there are actually counterexamples to some strong version of their conjecture, these counterexamples can easily be avoided with an appropriate modification. So it is of great interest to see if we can prove such a version of charge convexity conjecture in conformal field theory. With Daniel Harrow and with Jai Lee and Monica Khan, I have been able to derive related but different statement about asymptotic density of state for any unitary conformal field theory. I hope that the investigation along this line will enable us to prove or falsify the charge convexity conditions. So in this remark, I have tried to limit myself to statement where we can draw sharp boundaries between what is known and what is not known, about the boundary between what is possible and what is not possible in quantum theory of gravity, namely the boundary between the swampland and landscape. Although the scope of my remark has been limited, the evidence I have presented should already be sufficient to show that there are non-trivial constraints on the low energy limit of gravitational theory that cannot be captured by the standard Wilsonian paradigm. They prove the existence of the swampland. So now I'd like to call on the 4 panelists to make their remarks in the alphabetical order of their last names. I'd like to ask the audience to remain silent and to allow them to speak without interruption, as it would be good to hear their thought in a block of time in a coherent manner, and so that the panelists will not have excuse of not finishing their remark in the allocated 5 minutes. I will try to leave enough time for question and comment from the audience afterward. And before I call on the panelists, if there is any question from the audience now, I'll be happy to take them. Yes, please.
You gave some examples of what you described as constraints on the low energy limits of string theory. So one example is the absence of global symmetries. In our world, we have conservation of baryon number or a one-form magnetic charge because there are no monopoles that we've seen and so forth. So I'm wondering how many of these actually become constraints in the deep IR, or they just tell you about something that has to happen.
So in that particular case, so I didn't particularly call that as a precise constraint on low energy theories. So for example, the kind of constraint I gave was more, example was, for example, the existence of massless scalar field for parameters and the structure of the moduli space on that. That I think is a precise constraint on low energy theory. As absence of global symmetry by itself is not such constraint because there can be accidental symmetry just like B minus L symmetries, and which can be either gauged or violated in ultraviolet. So that by itself is not an example to demonstrate that. But I just wanted to demonstrate that there is a universal constraint on low energy theory, such as the structure of the moduli space. Okay? You have a question?
Yeah. If I'm living in a low energy theory, how am I supposed to know if there's a moduli space?
Well, you can measure you can see whether there is a scalar field or not.
Yeah, but I'm trying to remember, I'm trying to figure out how you would tell whether it was supposed to be.
I'm specifically talking about a case when we can formulate low energy theory in terms of Wilsonian point of view as a low energy effective Lagrangian. And we are specifically talking about whether there is a principle to exclude certain low energy effective Lagrangian. And that you can tell whether you have parameter or not.
Like, 10 or 19 parameters.
You have.
Yes, the scalars whose verse said that the couplings could be very heavy, in principle. Okay. So.
Well, so I said that there is when I only consider the case when there is exact parameters, adjustable parameters. Yes.
So I just want to poke at a minor, maybe minor thing, but you said whenever there's a parameter that's exactly marginal, let's say in ADS-CFT.
In the context of ADS-CFT.
There's a scalar field associated with it. That's not always true. It can be a boundary condition. It can be a double trace operator that's exactly marginal. It doesn't correspond to any new particle in the bulk, but instead a boundary condition, and it is a parameter. It's not dynamical there. It's a very extreme case, ADS-CFT, with this frozen boundary. But it has.
Let me see. So, for example, yeah, we should have this is a technical question. We have to discuss this. But so, for example, in the case of suppose you have a gauge field in the bulk, and you can consider changing boundary condition. But that can be, for example, generated by JJ bar perturbation on the boundary,
yeah,
for example.
It doesn't correspond.
So there are examples where change of boundary condition can be also controlled by adding exactly marginal operators.
No, it's an exactly marginal operator, but I'm saying it doesn't correspond to a new dynamical field in the bulk.
Ah, okay, that's what you're saying.
Yeah.
So there are cases when exactly marginal operator does not correspond to massless scalar field.
Double trace operations were missed early on in the duality because people thought.
Oh, okay, good. Yeah, thank you.
All it is, anyway, is known as a boundary condition.
Yeah, okay. Okay. So, but this is not a parameter in the bulk Lagrangian. That was what I was referring to. You're talking about the way that you impose boundary conditions. Other questions? So if not, I'd like to call on Nathaniel.
All right, Hiroshi, thanks very much. Also, thanks everyone for being here. So, of course, as the phenomenologist, true to form, I will be much less precise in what I have to say, but hope to keep it still interesting. And I should, of course, emphasize this is a particle theorist view. There are, of course, many other great particle theorists here who, in the questions and comments, I would encourage to share their perspectives. So if I can just briefly write here, and then I'll erase it to make room for the people to come after me. So to question one, I would say probably my answer is yes, but. Okay. Are they independent from purely IR constraints? And what I mean by that, right, we have this picture, I think, which has been advocated very nicely of the constraints coming from string theory that, we have this giant unbounded space of what Wilsonian effective field theory allows, and really, of course, there's some shining coming down from the UV theory, and this tells us there's parts of things that are allowed in EFT that are actually forbidden in a UV complete theory that contains gravity. But, at the same time that we've discovered a lot about what the shape of this lamppost looks like, at the same time, we've discovered an immense amount about what this looks like purely from infrared considerations. And so, in some sense, we were also naive, 20, 30 years ago, actually, about what it meant, what was allowed, what was speakable and unspeakable in Wilsonian EFT. And, great examples of that, of course, are positivity bounds, which are, proliferating in our understanding of them and their applications, just generally thinking about what infrared considerations of unitarity and causality tell us about the limits of the theory. And once we figure out how to include in non-gravitational EFTs, even if we just turn on Einstein gravity and we apply arguments of this sort, that begins to shape the space in very interesting ways. And so the question is, the but part is this what we should be thinking about, or really is the space of EFTs consistent with constraints that are emerged purely in the infrared from the EFT plus gravity? Do they already tell us that we had to live in that lamppost? And that would also be completely consistent. And so I think that's I think this is an open question, right? It would be great if there were absolute statements of things that could not conceivably be shown in the infrared. But I think we've learned there's been a lot of progress in pushing these boundaries, inwards. Okay, there's a lot more that remains to be done. We're certainly not to this point yet, but there's a question about where the line ends. Okay, so that's, I guess, what I want to say about 1. 2, which is going to connect to this in a second again. 2, my answer will not surprise you. Does anyone want to guess what my answer is to 2?
Yes, but.
Yes, but. Okay. Empiricism for the win. Okay. Okay. So the first part is actually not but at all. So even if the universal constraints on low energy limits of string theory were purely reproducible from the IR, the constraints that we identify in string theory are. So you might say, if they're reproduced purely by IR arguments, the string constraints would never be of added relevance to particle physics and cosmology, but that's not nearly true, right? One of the things that's actually sparked, I think, a lot of this attempt to hem in from the infrared this space is understanding that there are constraints in the UV that we wouldn't have imagined, and then trying to be very clever about understanding how we could reconceive them from the infrared, right? So even if the space of constraints turns out to be the same from top down and bottom up, knowing that there are top-down constraints, they're somehow much easier to see. That has immense value. And so that, in fact, teaches us new ways just of constraining field theory, right? Arguments we should bring to bear. So that's.
This UV duality.
Arcadia, I have to. Yeah. Okay. No, this is the Arcadi rule. The Arcadi rule. We're enforcing the Arcadi rule. Okay. So I'd say that's a positive thing. But I would say, in which case, I think it's inevitable that the constraints are going to be relevant. So then it's a question of degree. And 2 of the degrees that I want to ask that are particularly interesting to me, one is, do they lead to real surprises from an effective field theorist perspective? I'll say what that means in a second. And are they truly persistent in the infrared? And Henry got at this a little bit with this very nice question that we have accidental symmetries that, to experimental approximation are exact. So if they're broken by an arbitrarily small amount, maybe that's not useful to us. But I actually have an even different notion of persistence that I want to get to. So the question about do they lead to surprises, there's something as a particle theorist, so the constraints could emerge, we could understand them from the UV, the IR. The question is, what do we do about them? Do they teach us something new, new ways to do things that we wouldn't have known before? And there are things that could be true, but we need to understand the conjectures better. So one example is, we know in the WDC, there's a statement that, the charge in units of the gauge coupling, is greater than the charge to mass ratio of some appropriate particle. And there's an interesting point that was observed by Grant and Cliff Chung some time ago, that if you think about these quantities from the perspective of effective field theory, this is only logarithmically dependent on UV scales, and this is, if it's a scalar, as a mass, is linearly dependent on UV scales. And so there's an interesting question: as you vary, intermediate scales or thresholds in the theory, does that somehow give you a surprising constraint? Does it, for example, force, in order to maintain this inequality, as you vary parameters in the theory, does it somehow force parameters to conspire to keep a mass small? And if that's true, if that happens in real UV examples, that's an amazing violation of naturalness expectations, which is very useful to a particle theorist. But it may not be true. It may be that actually when you write down a string theory construction in which this is satisfied, these things actually depend in a correlated way on the intermediate scales so that nothing ever surprising results. And so to understand whether surprises happen that are very relevant to particle physics, I think it would actually be great to see very detailed examples of how the conjectures play out in the string construction to know whether particle physics surprises can emerge. The question of persistence is there not just, maybe we're happy with accidental symmetries in the IR, but there are examples of, you can write down field theories which, when you formulate the theory, say in an unbroken phase, so these are known as clockwork for the aficionados among the audience. I'll give you a simple example. If you're thinking about the electric gravity conjecture, you can think about a theory with 2 U1s. I'll call them U1A and B. They're connected by some scalar that's charged under both. It carries charge Z under U1A and unit charge under U1B. We imagine Z is very large. And let's just imagine there's some particles of unit charge under A and B whose masses satisfy the weak gravity conjecture for the two of them. If the scalar that links the two U1s gets a VEV, then of course as it Higgses them down to a diagonal U1, and the effective gauge coupling of that massless U1 is, when Z is large, if they both have the same gauge coupling G, it's G over Z. Okay, so it's a much smaller effective gauge coupling. And then if you're in the infrared, and the unit charge particle of U1A carries unit charge into this massless U1. So from the infrared, if you encounter that particle, or if you encounter this gauge coupling, you say, well, the weak gravity conjecture leads me to expect new physics, at the scale, the magnetic weak gravity conjecture leads me to expect new physics at the scale G effective times n Planck. But of course, you then go up through that scale, nothing happens, and only at a much higher scale, G m Planck, do you encounter the rest of this. Right? So this is an example of a theory when I write it down, all the ingredients satisfy these conjectures, but in the Higgs phase, the infrared spectrum violates it. And so the question is that allowed or is it not allowed? And if it's allowed, then it's somewhat hard to know whether these conjectures will be persistent in the infrared, because I can appear to violate them parametrically, right? But maybe there's something really powerful in these conjectures that actually forbids this from happening. So it would be good to know if this is persistent or not. Okay, I'm sure I'm over time, but let me briefly go through. Okay, let me briefly do three. These I think were some of the non-trivial things I wanted to say. About three, I mean, I think this is the sort of obvious answer, but we've had these questions in particle physics and cosmology we've been grappling with for decades. The origin of the weak scale, the electroweak hierarchy problem, the strong CP problem, homogeneity and isotropy of the universe, the cosmological constant problem. For many of those problems, certainly the strong CP problem and the hierarchy problem, we've attempted to solve them as problems in the non-gravitational EFT, and I would say it's fair to say up until now we've failed, right? Now, if you're a particle theorist in the last decade, they've been very creative about trying to find new ways to solve these problems, but I don't think any of them look better than the old ways. And so the obvious question is the reason we failed that we failed to take into account the fact that there is gravity. And by including gravity, can you just give us new insight into these problems? And that's why I find all efforts, I think, to understand constraints coming in low energy theories coming from string theory is powerful and productive, and particle physicists should be paying attention to it because it is sort of the one big new tool we have to approach these problems. So it's not obvious to me how it's going to help us, but it's obvious that it's the one qualitative change in how we've perceived this problem that can bring something new. And so the last thing I would just do is I want to add a fourth question. So I know this is unfair to the rest of the people coming after me. And maybe I'll even ask Hiroshi to answer this. What string constraints can particle physics and cosmology try to test? So, I think we're in a period where we don't really need more conjectures. But we, and obviously, the conjectures we have, what we need to do is we need to find more evidence for them, as much evidence we can. We need to understand the subtleties as best as possible because they have great bearing for the infrared. But then, what is the great thing that you would ever hope to do is you would hope that you've done a Babe Ruth, you've called where the home run is, you've said that there's something that is possible or not possible, generic or non-generic, and then there's some measurement we can make, whether it be related to the discovery of new physics or properties of the standard model, that would be considered by many to be experimental verification. So we should think about that because that's exciting. Okay, thanks.
Okay, now you are entitled to ask questions. Thank you. Yeah, Arthur. Yeah.
No, just about this last one. I'm sorry that I did try to interrupt him like the rule, but I was not punished. So.
You don't know yet.
Not this time.
No, but because for me it's kind of the global problem is that say if there is this kind of UV IR duality in the pairs of gravity, then to say that everything, this kind of the test or whatever, is it would be in this sense. You're saying that this, say, IR test would be checking some UV?
Well, no, just the question would be, are what we call infrared considerations, consistency conditions alone enough to reproduce the same constraints that we get from the UV? So could I use analyticity, causality, unitarity, in the IR spectrum, my EFT plus even just Einstein gravity, or maybe Einstein gravity augmented with some...
Yeah, but it doesn't include duality then.
No, but you might hope that somehow this could be true because of dualities. But I just want to know. Regardless, I'm not speculating heavily. It's impressive to me that what we mean by the space of Wilsonian EFT has changed dramatically in the last 15 years, and I think it's going to keep changing. And the question is, how close does it get to that spotlight?
Steve, you said that particle physics solutions to the strong CP problem and the hierarchy problem have failed. The axion solution to the strong CP problem has failed because axions haven't been discovered?
No, good. So yeah, thank you for giving me the chance to moderate some of those strong claims. So I think the hierarchy problem, I would say, has largely failed, right? Where the order one solution should have come in has failed. You can build epicycles and Rube Goldberg devices, but it doesn't feel right. Okay. The strong CP problem, it's actually interesting. Whether or not it has failed, or whether or not our attempts have failed, actually comes a little bit down to infrared and EFT assumptions that we're making. So for example, you might say the axion is a failure because of the quality problem. And now there's the question of the quality problem. The fact that it requires a global symmetry of extreme quality. And as an effective field theorist, we might say that the manifestation of that violation of that global symmetry by quantum gravity is effectively reproduced by Planck suppressed operators. And if that's true, then of course it fails. But the question is that actually correct? Is the form of violation of the global symmetry from quantum gravity of that form, or is it always exponentially small? There's of course suggestive evidence, which Naomi will tell us about tomorrow, that in corners of the landscape where we can compute, the quality problem it doesn't seem to be necessarily as problematic as naive expectation. And so it might actually be that microscopic considerations, the ability to comprehensively answer the nature of the symmetry violation, rescue these solutions, which I think would also be interesting.
Okay, Miguel?
Yeah, I wanted to talk a little bit about the clockwork and that kind of loophole, right? It's related to whether there's a sublattice of gravity particles, so on and so forth. And so that's definitely realized in string theory, and the question is how big that number
how big is
it,
it,
right? Yeah. And so I think that the data that we have on that, it's mostly from perturbative corners of string theory. Okay, so it's just one corner. But for instance, to 4 dimensions, nobody has ever constructed a model where it's bigger than actually 42. So that's the
42 is still big, and of course, it's life, the universe, and everything. But
42, and the question is, what is the biggest that the sublattice can get?
Okay, Douglas Adams was a wise man.
But
that already is. But now can I chain together a few of those? So obviously, if I repeat the structure Z1, 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 if it's 42, I get 42 to the n.
Well, this is an example where you just have one guy. It has 42, right? It's not the same as, and of course you need, if you want to chain them relaxation-like, that's also difficult. It requires more structure than just.
And so the question there is, how much do we feel that this is a lamppost versus an indication of what's possible or not possible?
Well, in that regard, I think there's a very interesting paper by Wati, and so you guys wrote a paper, I think, last year where you have an example in 6 dimensions. It's not exactly the same, right? But they have an example, correct me if I'm wrong, where the charge lattice, like the first guy has charge 1, but the first massless guy, which is the thing you control well, has charge 600. Okay. Now that doesn't, it is, again, correct me if I'm wrong, but it could be a weak gravity guy of charge 1 or 2, massive guy, we don't know.
These are U1 charges.
These are U1 charges, It's just one U1, but the massless guy has charge 600.
Interesting. So somehow the mass is, mass
and this is very much away from perturbative.
But anyway, this is an excellent example of where the infrared provocation hopefully helps to sharpen some better understanding of that.
Yeah, so let me take the last one from Wati before moving on to the next
Great,
one.
thanks. Actually, this is a little bit related to Miguel's question, which is, you brought up the hierarchy problem and the cosmological constant problem as things that maybe string theory could try to solve. And I just want to ask what it would mean for string theory to solve those problems. Of course, for the cosmological constant, we have the possibility of the multiverse anthropic issue, but it seems to me that the only other way to solve those problems would be to rule out, like for instance for the hierarchy problem, if you're going to solve the fact that the Higgs mass is so small, you would need to sort of rule out the whole family of theories with bigger mass terms. And that seems very unlikely that we'll do that. So similar to this U1 that Miguel was mentioning, there are certain continuous parameters where if you get something that looks finely tuned, it's hard to prove that string theory leads to that unless you can rule out everything else. And I don't believe we'll rule out all the theories.
I agree. In theoretical frameworks where we've entered into a controlled EFT regime, and in that EFT regime you have a continuous family of parameters that varies the Higgs mass, then I think that's just a manifestation, that's evidence you give to people that in fact the problem is real. So, but something that would be more surprising, right, is, again, this question of what is there room for surprises is somehow something that from the infrared appears to be a violation of EFT logic, which assumes lack of correlation between these infrared mass scales. If in fact they are correlated in some way by consistency with some microscopic requirements, that would be a violation of IR EFT expectations that I think if you understood how it worked in the microscopic theory, I would call that a solution, even as a field theorist.
So you're imagining that such a surprise could tell us that the Higgs mass couldn't be 1,000 times bigger.
Exactly. And so therefore, even though it gets contributions from large scales, the large scales are forced to what looks like an infrared conspiracy, but in fact is, in a microscopic theory, just the result of some consistency.
Good. If I could just add one more comment. So at least in the cosmological constant case, we are pretty sure that's not the case.
Exactly.
Because we believe we have string theory solutions where it's hard to get small cosmological constant, but it's easy to get big ones.
And so there, for this, for the CC, EFT has failed so badly that it's very hard to imagine how even conspiracy would help you. There, it would have to be that somehow we are mistaken in thinking about how vacuum loops radiate or something. They would have to be something wackier, right, to make new progress. But I think the one, unsurprisingly, also given my interests, the one where I'm most enthusiastic for this is the hierarchy problem, where there seems to be room to rescue it in these interesting ways.
So are you saying, sorry, just a follow-up with one question. Are you saying that if string theory kind of generates an idea that you can then package as an official solution to one of these naturalist problems, regardless of the fact that there are other string theory back here which do not make use of this thing?
I wouldn't be, well, I might be intellectually committed to that over others, but I think, of course, at the end of the day, why, even in particle physics, why do we think about these problems? And why do we try to solve them? It's not so that we can sleep at night because we think we've solved them. It's so that we think that there is a promising direction for experimental tests, and we can focus, actual searches for new phenomena. And so the hope would be, okay, if this emerges in some string configuration and we understand how it works, we try to figure out what is the most promising observable. If there are none, then it falls in the category of things to help you to sleep at night. If there is something, no matter how remote, then we at least ask, can we build an experiment to check it? Right. So how we shape our theory priors, goodness knows. But if it gives us ever a productive way of thinking about new experiments, then that's why I'm here.
Okay, I think the answer is yes.
Yes, yeah. But we should aspire to start with. Okay. No.
Well, he's basically saying there's going to be others that don't fit.
Yeah, of course, absolutely. But the question is, if this then this is consistent with something that you thought was a problem that points in the direction of building an experiment, in the infinite space of experiments, that's not a bad place to try to build an experiment. So, okay. Before I surrender this, I just want to say, controversial last opinion, since I don't have to answer that one afterwards. I feel like sometimes the healthiest periods of particle physics and string theory have been when they were closer together, and so I'm really glad that we're all talking about this, so thank you.
Thank you. Well, thank you.
All right, so thanks, Nathaniel, for leaving your drawing up on the board, because I'm going to use that, actually. So, thanks for asking me to be a part of this panel. I'm really excited that there's more dialogue between particle physics folks and string folks, since I consider myself someone at the intersection of these two communities. And so, indeed, so for a long time, we have been conjecturing things about constraints on low energy EFTs motivated by string theory that falls under the broad landscape of the swampland. But, swampy things, without attaching too much meaning to it. But more broadly, this is about ruling things out. But there's another set of tools that we have available to us, which is more morally about ruling things in, at least subject to certain conjectures, and that's the bootstrap or bootstrap type methods. So I'm interested in putting these two ideas together. So that is, we have UV motivated criteria, mostly string constructions, but we can also ask about building things in the IR that may or may not be consistent, and then checking if they're consistent with what we think we know about the UV, or checking whether they're consistent with IR motivated criteria. So, in particular, aside from dispersion relations and all that, it's interesting to start thinking about bringing the tools of the modern amplitudes program to bear and putting them in conversation with the swampland program. So lately, I've been thinking a lot about this in terms of, can we ask the right question of the S matrix to somehow uniquely get string amplitudes out? Is there some broader space of objects that satisfy the mathematical miracles that string theory spectacularly does? And if we can find some other set of objects, can we then rule them out using IR consistency criteria? So one comment about the IR, let's see, that might be too far to the left, so let me just erase this. One comment about dispersion relations and all that in the IR is that we are still understanding the full set of IR consistency tools. So in particular, very little has been done to understand higher point perturbative unitarity. And I'll talk about this in my talk tomorrow, but we don't have a set of Legendre polynomials for 5 or 6 point scattering. So if someone comes up on the street and hands you a putative amplitude for quantum gravity that's at higher than 4 point, it's hard to immediately tell whether it's even consistent with perturbative unitarity, or whether it immediately fails. So this is an amplitudes, purely IR question that we need to understand more fully in order to even have a chance of bringing to bear all of this technology to saying things about the UV. But it's even worse than that, and so there's lots of room for progress. If someone hands you an amplitude and asks you, does this come from a causal theory? It's just some function of ST and U. There is not a well-defined algorithm to answer that binary question, yes or no. There are certain features of amplitudes that are hallmarks of them not coming from a causal theory, but the converse is not true. So understanding that would be better. I'll second Nathaniel's comment about, perhaps the swampland equals the set of IR consistent amplitudes. So perhaps, indeed, this spotlight does shine down on just the appropriate region of consistent IR EFTs. But we can also take this space to mean something else. We can take this space to mean not just the set of consistent EFTs, but what if we ask about the function space of all possible amplitudes? And we can ask, if we start building amplitudes in the IR, can we turn this spotlight the other way? If I start building functions in the IR, can I try and uniquely find string theory up in the UV without knowing about it beforehand? And one hope, or one hint that might be possible, is the fact that there are all these properties of string amplitudes, even at tree level, even at modest point, like 5 and 6 point, that are not as yet well understood 50, 60 years on. So I'll give you one example right now that won't be in my talk tomorrow, which is the fact that string amplitudes, in addition to poles, have all these so-called hidden zeros that Nima Arkhani-Hamed and company have just been telling us about in the recent papers. So at 4 point, this is trivial, right? So let me write down the Veneziano amplitude at 4 point. Let's do this for massless external states, just for simplicity. So we have poles in the S and T channels, and then at 4 point, the hidden zeros aren't so hidden. You can see them right here. When U equals minus an integer, the amplitude vanishes. But this simple observation persists at endpoint. So for example, at 5 point, you have hidden zeros at S51 minus S23 minus S34 equals one negative integer, and S23 minus S45 minus S51 equals another negative integer. Why does the amplitude vanish in string theory at those special kinematics? Is there some physical reason for this? we should seek one out because there's a simple two-line argument that the 4-point amplitude can be uniquely derived, if you didn't know it in advance, just from crossing symmetry, Regge scaling, the location of the poles, and, crucially, the location of the zeros. So I'll show you that right now because it's sort of a cute argument. So suppose, again, you have some amplitude at 4-point that is crossing invariant. Suppose also that it has exactly the Regge scaling behavior of string theory. Suppose it has poles on the integers. More on that later about relaxing that assumption. And suppose it has zeros at the negative integers. Okay, then it's simple to see that the function, viewed as a function in S, gamma minus S minus T over gamma minus S times A, let's define this as some function where T is just a parameter, it's a function in complex S. This function is analytic everywhere. It has no poles, we've gotten rid of them. It is entire, as I said, and it is bounded. So by Liouville's theorem, it is a constant as a function of t, and you can immediately set f of t equal to gamma of minus t just by crossing, and so you get the 4-point Veneziano amplitude for free. It's an interesting question of whether this simple argument can be generalized up to endpoint. It's harder. It probably needs extra information about the detailed structure of Regge bounds when you have more than just two Mandelstam variables. But this implies that we should seek to understand all the different properties of string theory that are even accessible as relatively low-hanging fruit that have been in the theory for 50, 60 years. The one other comment I'll make is that we don't yet understand the full set of IR consistency tools, or in general tools that are arguably fairly UV agnostic, even if they're not strictly in the IR. So for example, self-consistency of black hole physics. Famously, Bekenstein and Hawking found the black hole entropy without knowing about counting string microstates, right? You can get it essentially from GR. Same for the Wald entropy. It follows uniquely from the first law of black hole mechanics. Not only that, but I showed with Cliff a while ago that the weak gravity conjecture seems to be connected to self-consistency of black hole entropy, in that you can mechanically show that if you have some theory which is Einstein-Maxwell plus some higher derivative terms, these higher derivative terms, of course, induce corrections to the extremality bound of black holes, and they also induce corrections to the black hole entropy at fixed charges and masses. And it's an interesting fact that this shift in entropy, which goes like the shift in the action on shell on the black hole solution, also goes like the shift in the extremal charge to mass ratio. And you can get this, again, without any detailed knowledge of the UV. So the moral of the story here is that infrared physics might have an awful lot to teach us about swampland-like bounds, and we should continue to seek new ways of understanding these bounds that are maximally UV agnostic. So, thanks.
Thanks. Question, comments? Yeah, Arthur.
When you kind of give us this example, right? Implying this particular behavior, its behavior at large S in string theory, and of course if you say it goes all the way down, then I understand your argument, right? But while it could not be that it is S to the power, no, I mean, Regge behavior, but then something else.
Right. That's good. So this argument was very strong. I got an awful lot sort of immediately, but the cost was assuming quite detailed behavior about the Regge bound. And so you could be asking, what if it's S to the T minus epsilon rather than precisely S to the T, which was necessary to use Liouville's theorem. It comes at a slight cost, but not too steep a cost. You can show, using a slightly more involved argument, that as long as A goes to 0 in the Regge limit, with whatever power at fixed t less than 0, so indeed S to the T minus epsilon, you can again get the Veneziano amplitude at 4-point uniquely from the zeros. So that argument just takes more like 15 minutes rather than 2 lines. So
this would be more impressive as opposed to just properties of an entire function.
Yeah.
Sorry, of neuromorphic functions.
Yeah.
Entire. Which is really very limited to tree approximations.
Yes, yeah.
If there was some physics, there'd be zeros.
Right, right. No, but that's what I'm saying. We have no idea. I mean, for the one where n equals 0, right? This is just the Adler 0. So that one's not very interesting. But what the u equals minus 23 pole, why that should be 0, we don't know. But this is just an example. Another interesting example. So this is very much work in progress. But another interesting feature about string residues on the poles is that they have this beautiful factorization structure, right? So if you ask about the nth residue as a function of t, right? At n equals 0, it's 1. At n equals 1, it's 1 plus t. N equals 2, 1 plus t, 2 plus t, etc., right? So there's this fact that if you set t to one of its zeros on the nth residue, all the higher n residues also vanish. If you take that as some organizing principle, right? So if I write some amplitude as a dual resonance sum with completely arbitrary spectrum here, I'll be totally agnostic, some normalization, and some product with this nested zero structure, where t minus psi of k for some single function psi. So this has exactly that structure, but with arbitrary zeros and arbitrary spectrum. This plus crossing is enough to almost uniquely pick out string theory. In fact, you can fix the spectrum using this, and what you find is that mu of n equals just the Q-deformed integer. So string theory or the Kuhn amplitude. So this is the first time I've ever seen the spectrums derived from some other type of principle. So all I'm saying is the zeros, or this zeros on the residues, gives us some indication that there's more interesting mileage to be gotten out of understanding even tree-level amplitudes.
Okay. Thank you.
Thanks.
I think we should move on. So Eva?
Okay, so happy birthday, Hiroshi.
Thank you.
There's kind of a UVIR problem here, which is the longer you spend trying to decide what to say in 5 minutes, the worse it gets. But, okay, so I'm going to try to focus on things on which we can be constructive, and keying off of Nathaniel's yes but, I'm going to say yes and a certain amount. Not that this is improv, but it could be. So. Yes, of course, there are things that are universal constraints. These were reviewed this week in Miguel's and Irena's talks. It's certainly true that the Dine-Seiberg fact that the potential energy goes to 0 as we go to weak coupling in large radius is true. It's also very plausible that as you do that, if you carefully define what you mean, you get towers of states that come down. Okay, so that let's stipulate that. There's no problem there. And these are very interesting, particularly for string dualities and so on. The issue comes when you extrapolate wildly from a statement like that to statements here. And instead, I think the right question is really number 3 and number 4. And what I want to focus on in my 5 minutes is ways in which string theory does do this. It makes serious contact with cosmological observations without it being true that it's coming from on high from some, completely universal thing. Okay? So I don't want to bore people who know this with too many, familiar examples, although this is a very ongoing program. But I'll mention some of that while also sharing a relatively new one that I think we can all exploit. Before I go to do that, let me give one example that's more closer to such a connection, that I happened upon in my years in this field. which I wouldn't necessarily say is absolutely universal, but I think it might be that it is. And that is the question of whether the so-called m-squared, phi-squared model of inflation exists in UV complete theory. Okay. The reason to doubt that it exists started, as these things often do, from working out examples, and examples have been worked out in great detail, where instead of that, we find instead something more like a classic plateau potential with some funny, for example, some funny power of the inflaton field phi coming out of some long analysis. And there's various examples where this power becomes some other powers, p, but it inevitably happens that it's flattened compared to m squared phi squared. Okay, and why is that happening? It's not something very deep at all. It's just the fact that energetically, so in string theory we have many degrees of freedom, most of them heavy. Things tend to couple to each other, and once you take some putative m squared phi squared model and you couple it to other degrees of freedom, including heavy ones, and you do what you need to model inflation, you find that those heavy fields have an effect, and they tend to do the energetically favorable thing of flattening the potential. So this is an example. This is kind of a lesson you can abstract from serious studies of top-down string theory. It's an old one, but it has phenomenological relevance because of the famous RNS plot where m squared phi squared, well, at the time that we noticed this, it was still viable, but instead, as you do this flattening effect, the constraints experimentally go in this direction, and so does this flattening effect. By the way, multiple fields go in this direction, and this dynamics, which whose essence is just trivially simple, could be something universal. I doubt there's an exact model of this kind in string theory. Okay, but most of what string theory does in this interface, which is really a serious thing, is not to take some very universal thing and snap your fingers and turn it into some real constraint on phenomenology. What it's doing is more generating ideas. In fact, ironically, I think I can speak a little bit complementarily to the others in the sense that rather than shrinking what effective field theory practitioners, I mean, we're all physicists, we're all effective field theorists, and some such string theorists. Let's not over specialize. But anyway, rather than taking things people thought would have been true in effective field theory and eliminating them, what string theory has done in this area of, say, early universe cosmology more is actually expanded what people understand to be there in effective field theory. Okay, so this has observational consequences. The organization of studying the primordial perturbations, both at the Gaussian and non-Gaussian level, was very strongly informed by this. People started to develop an effective field theory that takes into account the kind of dynamics we find in string theory, where it's natural to understand that there's some relativistic dynamics on field space, and that was a direct stimulus for the then more complete effective field theory treatment of these observables. And by observables, I do mean literal observables that one can go and constrain meaningfully in the data. So there's things like this. There's, as was done here, there's the dynamics of cosmic strings, which is in that case certainly an existing idea, but the kinds of scales that emerge and the kinds of interactions they can have was very much informed by string theory. The meaning of the sign of any spatial curvature was also articulated most clearly by string theorists. And in this arena, there's just a long list of additional examples like oscillatory features and various things. Okay, so all of this is, really helpful in understanding what to do kind of on this spirit with this case, cosmological data. And, you know, there's a big program to really make the most of it, even just at the level of these things we already know about. And there's a lot of work to do there that requires a lot of, you know, theoretical creativity and dedication. But let me make a remark about a sort of relatively newer one that I'm personally fascinated by and that I think we can maybe discuss if people are interested, which is what I'll call non-perturbative non-Gaussianity. Okay, so what do I mean by that? Well, I don't know if you can't. Can people see? Okay. So, you know, we have some unknown probability distribution for scalar and tensor modes in the early universe, which would be obtained by, you know, integrating out anything that I'll call chi that we don't observe, times the square of the wave function for everybody that we don't know. Okay, so this is the thing whose moments we investigate in the data. And one interesting thing about it is the low point correlation functions, which is a large part of what people have focused on in this subject, doesn't by no means always carries the most information. So you can quantify that using relative entropy. And, you know, it's a UV sensitive question how this thing behaves, say, on the tail of the distribution. So you can define, you know, the field smoothed over some scale, and it may look Gaussian to good approximation, perturbatively near the mode of this distribution. And it's an interesting question what it's doing beyond that and to what extent there's enough data to capture features that are further out on the tail, and that can work in many different ways, some of which have been laid out, starting again from string theory, leading to some optimal estimator being derived by Kendrick Smith and people looking at it. But as you can see, there's an enormous, you know, space of ways this can work. But let me say something a little bit more specific, which is the following. If you have, so sometimes you can calculate this using semi-classics. So basically do this path integral, even the ones appropriate to defining the wave function, regardless of there being extra fields. And various groups, that includes Bond, Criminelli et al., some stuff we did at Stanford also, where one can, you know, in examples, at least one can calculate this and see what the strength of the effect can be, at least in those examples. Let me just give you, though, some intuition for why this can be an interesting effect, why it could come inspired from the way things work in string theory. And it's a kind of very open direction, okay, to flesh this out. It's a very interesting theory problem. It's also very interesting for those who think about what to do with large-scale structure and so on to formulate the right observables for this kind of thing. Okay, so just let me get to the example I want to mention, which is if for whatever reason you have a hyperbolic field space underlying the doesn't have to be a moduli space, but just some field space that is hyperbolic. That can happen because of low energy supersymmetry where that comes out. It can also happen if you have, say, hyperbolic extra dimensions, which is by far the most generic thing, and you have somebody moving around in that space. So if you have that, then as you can imagine, I mean, you know, that means that there's some exponential, I'm just going to say this in words, there's some exponential in the action of the QFT. And that's the kind of situation where you can have a very strong effect on the tail. It's very sensitive to this. So in some estimation, we found a tail that goes like at least in some toy model of this kind of thing, where there's some UV scale-up star, and you get essentially a power latte, or very, very heavy non-Gaussian. So it may be that this kind of thing can be ruled out instantly, that's sort of in the spirit of Nathaniel's thing, but it's, it's enticing because of the fact that indeed from the top down we often encounter this situation. Yeah, and it's an interesting challenge, but again, it's going to be model dependent. There is a beautiful paper by Daniel Green et al. Showing how UV sensitive it is in various regimes in the general case. So this again seems to be one of those things where there's an interplay happening between the areas. I don't know where I am on time. Let me say one more thing, if that's okay, which is, to me, the thing to do that's closest to this, but not exactly this, is to not necessarily think about what's universal, but instead to think about what's kind of massively generic in the theory. Okay, and this is where, you can get into trouble if you say something's universal, but if you ask, what is the, by some, let's say, counting measure of topologies, what's the typical thing that string theory does? Well, one thing that isn't anything new is axions. They're as generic, if not more so than, certainly more generic than Einstein gravity is. But the other thing that, I've already harped on several times this week is the fact that negative curvature internal dimensions is infinitely more generic than, say, the Calabi-Yau's that gives you supersymmetry. And there's a huge amount one could do to look into, okay, this is not I'm not saying there don't exist Calabi-Yau's, but this is almost always what string theory does, because it's a higher dimensional theory of gravity. And these spaces have favorable properties like rigidity, and the stabilization to de Sitter is as simple as it gets, and we have parametric limits increasing the control of that. And one could do the same kind of exercise people did a lot with Calabi-Yau's to see what is the consequential phenomenology in this case. But it's not based on a claim that it's the only thing. It's based on the reality that we have many kinds of behaviors in string theory. And the main message I want to make is that the utility for string theory combined with effective field theory and observations being useful does not hinge on a yes answer to this. It just doesn't. So let me stop there.
Thank you. Any comment, question? Yeah.
So since you're focusing on generic things that you get from string theory, one thing that, if you don't work hard not to get, you do get, and for instance, you do get in the hyperbolic manifolds and stuff, is you get fifth forces, right? Because the stabilization for the volume modulus, right? You get a bunch of potentials of order 1, so you typically get the scalar, which is very nice.
I really want to understand what you're saying, Miguel, but I would have not said that, so let's talk quickly. So there's some three-term structure there, which is negative curvature, Casimir, and flux. This one is stabilized to be heavy. Everybody else is rigid and stabilized at the KK scale of the manifold. Right?
The volume modulus there is very, the mass of it is very small, right? It's for the Hubble. If the three terms of the potential are comparable, right?
No, it doesn't have to be of order Hubble. You tune to get Hubble to be small, and that does not tune the mass to be small. You would have to do something more to tune the mass to be small.
What you can do is you can tune it, right, so that the height of the minimum is much smaller than the height of the barrier, in which case you decouple the two things, right? But if you don't, if you just write three terms that give you a minimum, typically the size of the minimum is comparable to the size of the barrier, which means that the mass of it is comparable to Hubble.
There are definitely regimes where you could have both. I'm just saying if you do the job of fine-tuning Hubble to be super small, it would take another tune to somehow make the mass small. That's all I'm saying. I'm not saying anything new. Yeah. You could have. I don't think we disagree. I'm just though saying that it is a huge tune to get Hubble to be small, right?
Yeah,
so you don't necessarily want to double that. But go ahead. What was your question?
What I was saying is, like, in general, as you're saying, we need at least one tuning to make, Hubble small, because it's very small. And then, the generic thing with just that tuning would have fifth forces that we don't see. So.
Well, I think you would say that about anything in the, it doesn't depend on this particular model, right?
Yeah.
But I do think that when we know the value of the CC, it is truly tiny, right? So there is I would say we swallow one tuning and not an unnecessary one, but from this point of view of genericity. But we could discuss more. Yeah, I'd like to hear what you're saying better.
Okay.
Yeah.
Yes.
Yeah, I have also a quick question that sort of goes morally in a similar direction. Like one of the things we learned from string theory with Calabi-Yau is that, for example, the standard model, getting that one is super non-generic. One can get it, or one can get close to it, but super non-generic. And sort of how would you cope with your strategy?
It would be the same sort of stuff, some intersecting branes with some singularity. The thing that's neat about these, which phenomenologists said first, so there was a paper by Nemanja Kaliper, Glenn Starkman, Mark Trodden, and somebody else whose name they won't watch this, I forget. But they stressed a lot of these things, just not with the string theory overlay, but the fact that you can have a volume that's large, but the mass scale is not controlled by its nth root, or in this case, its seventh root. Instead, it's controlled by the curvature radius. Okay, so things are just naturally heavier in this scenario, which puts them more out of reach of experiments. But it's good for the fact that we don't find much in the almost everything except the Higgs that is light, right, is light for a reason, and there's not evidence for anything more than that. And it was in the period when people were talking about large extra dimensions that these authors talked about that, but in the context of this case of negative sexual curvatures, let's say. And you can see there the scales are such that it's kind of like one of those, you can consider at least a case where the scales are like people have been considering in these large dimension scenarios, except, again, a bit more stable and a bit more, consistent with not seeing anything new, say, at the LHC because of this distinction that the KK masses are heavier than you would have thought compared to the volume, which is the thing that controls the Planck scale. So it's that kind of thing. I don't have any specific claims about the phenomenology of this, except I think it could be done much more. We were interested in this in part because it's an uplift of ADS-CFT. It's a direct uplift of the M2 brane theory, and that can give us a handle on the more kind of conceptual questions in the field.
I wanted to understand the context of it, because you asked this in the context of your principle about genericity.
Yeah, exactly. So
if the genericity, my understanding is that if the genericity can be principle, then standard model seems to contradict.
No, if genericity is a principle, and I think this comes back maybe to Wadi's comment, though you can correct me if I'm misattributing. Yeah, almost everything string theory does is highly curved and highly, it's definitely special to forget about the standard model, special to get this small a CC. It is. So when I say genericity, I mean everybody should be conditioning on those knowns, right? And then having conditioned on those, we don't need to necessarily pay any additional price. So it's, you would have the same question about any kind of compactification. So why fixate on a very special class?
Yeah, I just want to follow up on this question of whether the standard model is non-generic or not. I mean, we don't understand yet these hyperbolic compactifications, I think, well enough to understand what's generic in terms of a gauge group. But at least for supersymmetric compactifications from F theory, some gauge group is generic, and breaking of that by fluxes is generic. So it's not actually obvious to me that the standard model is non-generic in that sense. I mean, we've been looking at like these E7s, which are highly generic in the F-theory landscape, which get broken by fluxes, which are fairly generic. So I think there could be a story where actually if you look at, the possible gauge groups coming from typical compactifications, the standard model might not actually be that non-generic. And I could even imagine in the hyperbolic compactifications, if you include singularities that give gauge groups, you could have a similar thing where there's rigid gauge groups and they might get broken.
Yeah, could well be.
So, just pushing back on that notion that it's somehow obviously highly non-generic.
Okay, thank you. I think I need to leave some time for Irene before we go to the tea time, so please, Irene. Thank you.
Now, thank you, Hiroshi, for organizing this. I think it's super nice. I really like a different question. I think it's super nice way to structure. Okay, so quickly, yes, I think so. Okay, I'm actually happy to see, I was thinking of more examples to try to argue for this, because for me this is the most important one, it's like the beginning of having this discussion, but I'm very happy to see that we kind of agree actually, and I think I like the example that Hiroshi gave. I think they are more like, I don't know, for example, if you allow me to have high dimensions, a lot of supersymmetry and so on, we know that not every gauge group can be realized in string theory. So this, I think, the fact that we think that the answer is yes, I think is amazing, because then it's a matter of trying to continue and see how far we can get. No? I want to say that the swampland all the activity really came as a counter reaction to the idea that you have a huge landscape, so everything will be allowed, so it doesn't matter what model you have, you will find a way to realize it in string theory, which I think is very dangerous. And the whole point is trying to say, okay, no, not everything goes. There are proof of principles of things that cannot be UV completed, and I think there is a change of attitude, not just from the swampland, but also amplitudes, matrix bootstrap. There are more and more emphasis on trying to understand what are the constraints from UV completion. Now, the question is, okay, even if there are constraints, how useful they are, right? And that's what we try to do. And that's what we are trying to investigate. So here, from the swampland, there are different types of constraints. So yesterday, I was discussing constraints that come from these towers of states. Because for me, this is one of the most universal things that you get from string theory. So it's a matter of what can you learn from that. The easiest thing you can learn is try to determine what is the cutoff of the theory, because once you have this infinite tower of states, you are gonna, quantum gravitational effects are going to become important. So you want to quantify this very well. And in a sense, it's still surprising, from IR perspective, because, it's clearly that the EFT is going to break down at some scale, but if you can determine that scale in terms of EFT data, it's something new that typically you cannot just predict from the IR. Okay, so the whole point here, what we are seeing is that depending what is the EFT that you have, in certain cases, maybe you are too close to engineer something that gravity doesn't like, because maybe you are trying to decouple sectors that you cannot decouple, generate global symmetries and so on, and this can become much lower than the Planck scale. So that's one thing. I think this is just the first part. Of course, I think the second step would be not just ruling out theories, as Eva was saying, but trying to find correlations, as Nathaniel remarked. Like, okay, in addition to giving a constraint on the cutoff, can you understand whether there are correlations? Like, okay, if I have this, do I need to have another thing? No? It's not necessarily about genericity, but more about, okay, if I already impose that I have the standard model, for example, regardless of whether it's generic or not in the landscape, is there any other thing that I need to have, and then I can try to test, right? So these are the type of correlations we are looking for. I wanted to mention, since I didn't mention yesterday, global symmetry. So the absence of global symmetry is a bit unpopular for phenomenology because of this message that since, I don't know, maybe I can break it at a high scale, so what implication does it have? I think this is actually not fair. Because precisely now we are living a time in which the notion of symmetry, right, is being generalized. There are many types of global symmetries. And this is true that for ordinary symmetries, I don't think the statement is very powerful. But when you think of other type of symmetries, only this alone can already teach you a lot. Okay? So, for example, when we are discussing all these generalized symmetries, basically you have charges that are carried by higher dimensional objects and so on. These symmetries are broken by the existence of states. Okay? It's not just like having a local operator that might be suppressed. You have new states. And that's already something, but the point is that sometimes you can study more detail what are these new states that you need to have to break the symmetries, and sometimes you might also be lucky and maybe those objects, those states are inconsistent or are anomalous or something goes wrong with them, which means that there is no way to get rid of the symmetry. So in those cases, there are examples of this in the literature and also by Miguel here, like you can really say that that theory is not just a matter of having a low cutoff. That theory cannot be UV competitive because there is no way to get rid of that global symmetry. Okay, so this is more like a yes and no answer. So we have examples of this in supersymmetric theories, but a priori there is no reason why it cannot happen also in non-supersymmetric ones, and that's I think an avenue to explore more in the future. Now the other one, and then I will finish. I try to be brief. Are -1 for symmetry, so this was actually mentioned a bit by Hiroshi at the beginning. This is kind of a generalization of this. Now the charge is carried by the entire space-time, so this is like having some free parameter in your theory. This is something which has not been explored much, not only from the pheno side, but also in the formal side. We have to understand much better how to define these things and so on. But I think it's a very promising avenue because, like, especially for all these questions on naturalness, hierarchy issues, and so on, you are asking about values of the parameters, right? Like assuming you have different values, they are free, and which one is natural, and so on. So, in the end, it's like asking, how you are breaking these -1 for symmetries, okay? So, for example, the strong CP problem, you can reformulate it as saying that you have a problem if you have an exact -1 for global symmetry in your theory, which would be this theta term. If you gauge it, then it's like adding an axion that couples to the trace of F shares. This would be the current of the -1 for symmetry. So the existence of the axion, you can understand it as a way to get rid of this symmetry, so it's a possible solution. And then quality problems and these type of things are also related to how many -1 for symmetries I have and how actually they are correlated and how I can break the other combinations. And then if you break it, of course you can also break, it's like fixing the value to some concrete, fixing the parameter to some concrete value, like in tadpole conditions and things like this, which means that there is no problem to start with either because it has just one value, right? So I also wonder, I don't know, if these type of things can be done more generally for other naturalness issues, like can we say anything about the Higgs, can we say anything about the CC, and we reformulate all these fine-tunings in this language, and then try to quantify how much you break these symmetries to understand what these values can be. So I think this is another possible avenue, and I think I'm going to stop because I don't want to take more time, so that's fine for me.
Thank you. Questions, comments? All clear?
I guess I'm drawing you on the question of the generalized symmetries, and this is, they're maybe the breaking is more definitive than the IR. But I guess if I have a higher form symmetry, I could break it with very, very heavy charged particles, right? And so in infrared, all I have is some imprint on the Wilson line of the theory, but there's almost no IR observables, right? So it seems to me that is, in the far infrared, plausibly as innocuous as breaking a zero form symmetry.
Yeah, the thing is that, for instance, for the 1-4 global symmetry, that's precisely what gives rise to the weak gravity conjecture, right? Then you say, okay, how much you break it? That means that you have to have an upper bound on the mass of the particle, and you can actually re-understand the weak gravity conjecture as a way to quantify that these symmetries have to be broken before reaching the Planck scale. So that's, yeah, exactly. It's like the type of surprises, right, that you were talking here, that does not allow you to get too close to restore the global symmetry and therefore puts bounds on these parameters.
Do you feel like it gets, I mean, one of the issues, of course, in trying to make the weak gravity conjecture phenomenological is we don't know if this should be satisfied by particles or black holes or who has to satisfy it, right? It's a little ambiguous in proofs of, or attempted proofs of the conjecture. Does thinking about it as a constant, in relation to generalized symmetries, does that help at all, or
I think so, because the point is that whether they are particles or black holes and so on, it depends of, for me, I think it depends on where you are in the moduli space, in the sense of whether you are at weak coupling, so you are close to restore a symmetry, and therefore you need to have physics that is below the Planck scale to avoid, so the cutoff has to go down, and therefore you are going to have physics like masses that become very small and go to zero, or you are like in the middle, so that you are very far, like the symmetry is super broken, and then, I mean, it doesn't matter, and you can have black holes just satisfying the weak gravity. So that's why, I mean, I think reformulating this way is useful, because then it also puts in context, no, like all these subtleties, like, okay, when, no, I mean, maybe it's not a yes or no answer, it depends, like you have to formulate better how much you have to break the symmetries to understand when you have the physics in the IR, no, and it really becomes a constraint in the IR versus just a constraint on the black holes.
Okay, yeah.
Just perhaps like to elaborate a little bit. So sometimes what can happen is that the object that you introduce to break the generalized symmetry is inconsistent, has an anomaly in its work volume theorem. You can maybe analyze this without knowing too many details about the object, whether it's a black hole or not. And if that's the case, then you throw the whole theory to the trash can. Okay? So that way, indirectly, you put constraints in the IR. And this is what Irina was mentioning, for instance, with theories with 16 supercharges in 8 dimensions, 9 dimensions. There's the number of vector fields that you can get in string theory is 1, 9, and 17. And from looking at these things, you get the constraint that the number of vector modules is 1 modulo 8, which matches.
Okay. Anybody else? So we can also take questions or comments on any of the remarks that have been given. Yes, what?
Yeah, I just wanted to follow up actually a little bit on the thing that Eva brought up, which I agree with very much, which is that the idea of
before that, let's actually
So Eva brought up this issue of genericity. I think is a really important and complementary idea to bring into this question of constraints. Yes. And of course, none of us have any idea how to solve the measure problem in string theory or in cosmology, but as Eva said, looking at just a counting measure on various things can give you a lot of interesting information that might start to address some of these questions. So we talked a little about the standard model, but I just wanted to mention a couple things related to the questions that Nathaniel brought up about the CC and the hierarchy problem in that regard. So I think for cosmology, the work of the Cornell group, where they found that it's actually not as exponentially hard as you might have thought to get a small CC, but by solving some system of Diophantine equations in a polynomially hard way, that's sort of a hint that maybe that distribution, that discrete distribution, is not as bad as we might have thought for the CC problem. And I could imagine some similar statement where, in this discussion we had earlier, it seems very unlikely to me that we're going to rule out a theory that looks like the standard model but has a Higgs mass of above a TeV. But I could imagine that it's not as hard as you might think to get a solution that looks like the standard model where it just so happens that the negative mass squared is relatively small compared to the Planck scale. And so would you view that as a satisfactory?
Yeah, if you could tell, right, because we assume basically a flat, log flat distributions, and that's how we have our notion of genericity from the IR. And if you could tell me that from the UV we have a much better understanding of distribution and it is not that, that would also be very extremely satisfying.
Great. And I guess one other question related to this, both to you and to Grant, from the top bottom up sort of people. I could imagine low energy ways of getting access to the constraints. Do you have any thoughts about how you might use low energy methods to get access to the measure?
I think, to me, by definition, it's impossible.
Yeah.
Maybe Grant's more optimistic.
A challenge for you.
I don't know that I would say any constraint is by definition impossible, but I don't have any ideas on getting access to the measure from low energy at present.
Thanks.
Okay. Any other questions, comments?
had a brief one.
Yeah, please.
Just on the subject of generosity. So I agree with all the points that have been made about generosity so far, and also Irina's point that maybe that's the wrong question in the string context. So if we're thinking about, the low energy 4D point of view, the standard model is extremely non-generic in the space of all field theories in 4D. But that doesn't matter because we understand well how to write it down, right? So something I don't think we understand well how to do in string theory yet is how to characterize which string solutions are going to look close to the physics we want, whether that's cosmology or particle physics. And it may be that there's actually a lot of correlated structure and a lot of constraints within that subclass of solutions that we just have not been able to explore yet.
Yeah. Thank you. Any other questions, comments? Okay. If not, thank you everyone.